Greetings. We were discussing about sampling variations, right? From population, we will always take a sample, and this is the data that we practically get. And whatever the results that we are getting from this data after doing the computations, these results will be used to generalize the findings for the entire population. So what we are interested in is the results on population. Those results are called as parameters. For population, they are called as parameters. But we cannot directly get parameters. What we would get is statistics. The results that we are finding on sample data are called as statistics. Right? So because we will be evaluating or we will be inferencing the results for parameters using statistics, we call this as inferential, this process as inferential statistics. Inferencing results for population or generalizing the findings for population. But when we do this, because we are tend to apply sampling techniques, which is always by default SRS technique. SRS is nothing but simple random sampling, which is a probability technique. The chance of getting the same sample would be completely, right? I mean, it's very less. The chance of getting same sample is very less. That means when we are repeating the same task or when multiple people are working on the same task, we will not get same result. Why? Because samples are varying. So inferential statistics, when we apply that concept, we're analyzing or generalizing the findings for population, we will get different results or different parameter estimations based on the different samples that we are working with. Right? So this is the problem. And to overcome this, central limit theorem basically helped statisticians when they analyzed this data, they found certain interesting facts. And that's basically defined as central limit theorem. So what we assumed is we will have multiple samples for a given problem and we will find statistics. X bar 1, X bar 2, X bar 3. So we are basically, see, whenever we say statistics, it's always about finding the first moment for the given data set, which is the representation, right? Mean. Mean is like representation of your data. So the primary statistic that we will be working on is mean only. And using that, we will have to basically estimate mu, which is population parameter. So when this data is being analyzed from different samples that we collected, right? When we are analyzing this, it was observed that this data is always following normal distribution, irrespective of what your population data is all about. Okay. So this is your population data. From here, we will take sample data. And from the sample data, we calculate statistics. But when we take multiple samples, we get different data, right? Different data in samples. So different statistics. We will be working with only one statistic because that is what we developed, we created. But like us, there might be many people who are working on the same problem. They may get a different statistic. So this single value that we are getting, that we are working with, is coming from a data which follows normal distribution. That is the underlying objective or underlying finding of central limit theorem. So to understand the characteristics of this random variable, this becomes your continuous random variable. And it is also said that it follows normal distribution. That's what central limit theorem proves. So when I have a normally distributed data, I'm trying to find out its properties, mu and sigma, because entire distribution is defined by these two parameters only, isn't it? First moment is the center, which talks about the peak, and second moment talks about the spread. So this sample means properties is what I'm interested in. So when we calculated the first moment on the sample means, it was always observed that you get mu, which is nothing but mean of the sample means will give us population mean. All right. So that is mean of sample means. These are all means, right? Sample statistics. This will always give me mu, which is population parameter. Okay. From this. So the center that we are interested in for this entire data set is mu. But what we got is one statistic. Now, using the second moment, I would say at how much deviation this mean was calculated. Standard deviation, right? That means how many variations, how many standard deviation variations is the value away from the center. Remember, we talked about normal distribution. If I have mu, but what we are getting is x bar, then when we are calculating, we were calculating to achieve mu, but we got this. That means there is some error in our estimations. We call this as error or deviation. Like that, there are many statistics that different people have calculated, right? So I am looking at, if I'm looking at this as the data set, then I'm looking at on an average, what is this variation? That is nothing but your second moment business decision, right? Variance or standard deviation. So if I consider this as the continuous random variable, then I want to identify what is this variation. And that's called as standard error, because that is the error in our estimation. On an average, we are finding out the variation. And this is calculated as sigma by square root of n, where the small n refers to the sample size that we are taking here, right? The sample sizes that we are taking here. In our sample, how many records are there? Okay, that's your sample size. Why? Because when you calculate variance, what is the variance formula or standard deviation formula? Formula, guys. Hmm. Formula of variance. Yeah, go ahead, please.
Sigma of x minus n.
Sigma of x minus
Mu by L.
which n?
Capital N.
Capital N. This is square, right? Variance. I'm saying variance. Okay. What about s square? What is small s square? What is small s square? This is population standard deviation or population variance. This is sample statistic. This is sample variance. What is the formula for sample variance?
Sigma of x minus x bar whole square by n minus 1.
Yes. Which n?
Small n minus 1.
Small n minus 1. So if you see in variance, we have this variation in the formula also. Variance itself is talking about variation. And here we have degrees of freedom in the denominator. Okay. That means depending on the sample size, our variations will depend. Now, what does that mean? Okay, let me go back to the previous drawing. This one. If you look at the example, okay, let's talk about this example. I see, right, people are widely spread. I'm taking a sample. Okay. So I get this record 1, 2, 3, 4. So I don't get this person. Green or whatever that color is, right? So green color, I'm not able to get. Now let's say I'm taking another sample, same size, or maybe I'll take only 3 people out of this, right? If my sample size is less, if n is less, what is happening? I would get too much of variation between the samples. Making sense? If I take a smaller sample, let's say I'm only using 3 people, right? 3 people sample, then I get blue, black, orange or brown. Here I might get green, right? And then this dark blue or light blue, whatever that is. And maybe I get brown. Here I might get green, blue, and blue again, right? Here I might get white, black, and then blue. So when you look at this samples, right, you clearly see that there is a huge difference between samples, isn't it? Now remember, we want results for this, but if your samples are less and if you find so much of variation, how will you be able to generalize the results for population? No, right? You cannot. What we need is a response which is closer to this population. And for that, what if I take a larger sample? If I take a larger sample, maybe I'll take 10 people, not 3, but I'll take 10 people. Then I will be able to capture all those variations within the population, isn't it? And if I take another sample with 10 people, the variation between these two is also reduced, isn't it? If you want to imagine this, let's say this is my population. I'm writing my data points like this, okay? Imagine these are all different people coming from different parts of the country. India, let's say India. Okay. Now what I'm doing is taking a smaller sample. So this is my sample. If I take another sample, maybe I'll take here. I'll take another sample here. I'll take another sample here. So you can see the data points are completely different in this compared to this, isn't it? So the results that I'm getting here will be completely different from this one or this one or this one. But what if I use a larger sample? I'll take a larger sample like this. One sample. This is second sample. This is third sample. So now what is happening is there's a lot of overlapping of data points within the samples as well. Right? That means the results that I'm getting from these 3 samples will be closer. There'll not be too much variation between them. Okay? That is the variance that we are speaking about. How is each data point different from the center that we are calculating? So it is definitely getting influenced by the degrees of freedom that we are using in our formula, n, sample size, right? So larger sample sizes reduce the standard error. Variations will be reduced. Remember this point. And thanks to this concept, we will basically now understand that what we want is mu, but what we got is sample, right? What we got is the sample statistic. But we know that there is a standard error. We are generalizing, right? So we found standard error, which is sigma by square root of n for any sample statistic that you found. It could be anything, right? We don't know. You calculated on the sample data and received this. But if you would have worked on a different sample, you would have got a different result. So we are generalizing that variation in our calculation. That is your standard error. So if I add this error, then I will go to the population that I'm interested in, right? So this is the formula. So it's called as point estimate, and the variations are there above or below, right? So I'll say plus or minus your standard error of mean. Okay, this is your population parameter. But what we will get is an interval. We have to generalize because we don't know whether this will be the result or this will be the result. So we are covering both and saying the value will fall in this region. This is the point of this is the kind of variation on an average we are getting, right? This is the kind of variation that we are getting. So whatever the values that you're finding will fall within this range from the mean. That's interval which we are defining. This is for a continuous random variable. And for continuous random variable, the probability associated with a single value is 0. Hence, we calculate or estimate the value in probability in a range. And we discussed that the range may vary depending on the confidence that we come up with. And the formula is extended to this, where your confidence value is added. Confidence component is added. So Z value with standard error. Now, if I know Z value, I will be able to identify the region of our interest, which is either 95%, 90%, or 99%. This defines my confidence when I am estimating a result. What we do when we calculate, we get probably X bar, right? But it may vary. So what we do, we calculate the deviation that we are getting, right? Sigma by square root of n. But how confident are you that your true value will fall in this range, right? So that confidence is the component that we are adding here, and depending on the confidence, we will alter the range for this point estimate. Larger the area, then more the chance you have that the true value falls in that range. This increases the confidence. But again, we will have to draw a line because you cannot go 100%. 100% means continuous value. This infinite possibilities are there, right? You cannot say 100%. So the industry standard tells 95% is an appropriate area of our interest for any business problem. Unless until you are dealing with life-threatening businesses like healthcare or aviations, or you talk about finance sectors, where your confidence has to be more. Though the range may be larger, the area under this calculated area, right, the region would be more, 99%. But because we are dealing with life threatening or very, very context sensitive business areas, the range has to be more. In general business cases, it could be 80% also. You don't need 90%. It could be like 80% in let's say manufacturing sector, which basically manufactures, like say, water bottles or some kind of pens or pencils, right? They are not life threatening business areas. So the cost of variation is not much in such cases. So businesses don't emphasize on streamlining the processes. So in such case, a lot of wastage goes, but that is okay. All right. So this is the concept of confidence interval. Now, I ask you to by heart the values of Z at 1 minus alpha. So we are basically assuming that the sample statistic that we are calculating is coming from a continuous random variable. Sample statistic is a value which comes from a variable which is identified as always normal, thanks to central limit theorem. Because it is normal, I will be able to compare it with Z. Right? So, in order to find the confidence, the region of interest, we need to find the Z values here to start with. Why? Because we know that if I know Z, then we can calculate the confidence region for X also. They are normally distributed. The area under the curve would be same. So previously we basically know the value and we calculated the cumulative distribution, the left side part. Now we know the confidence, that is, we know the region of interest. We need to find this Z values. It is symmetric across the center. So this becomes minus Z, this becomes plus Z. I asked you to by heart this, calculate this values. So tell me, what is Z at 95%? I asked you to by heart it. Z at 95%. It is given here.
1.96.
Yeah, it is given there, 1.96. Okay, now tell me, what is the Z value of 0.95?
1.96.
No.
Still the same.
No.
Yes.
Sorry?
Still the same 1.96.
No, 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 no. It is not 1.96. Remember, I'm giving percentage here, I'm giving decimals here. Draw it, draw it. Draw this bell curve and see the area and then say, what is that? Zero 0.95 means area under the curve. Towards the left side portion. When I say 95%, I am saying this is the 95%. But when I say 0.95, it basically means the area under the curve from here to the left side. This is probability, right? Area under the curve. So this entire region is 0.95. Yeah. So that what does that mean? How much space is left out here, this side?
Just
Five.
0.5.
5%.
What does this alpha become now? If this is 5%, what is alpha?
0.05.
No, alpha. This area is 1 minus, okay. This area is 1 minus alpha. Outside regions is what you will get as alpha. It is symmetric. So this is alpha by 2. This is alpha by 2. This is alpha by 2 is 5%. So what is alpha? 10%. No?
So
That means what is 1 minus alpha?
90%.
90%. So I'm asking, what is the 90% Z value, that too at plus Z?
1.65.
Plus 1.65, or we'll say plus 1.645 manual calculations. If I would have set Z at 0.975, then what will I get?
$1.96, 95%.
plus 1.96. If I say 0 at Z at 0.025, then this becomes minus 1.96. Here, if I say Z at 0.05, then this becomes minus 1.645. Similarly, if I say Z at 0.005, 005. That's basically calculated for 99%. So this is negative value of 99%, which is
575.
2.575. Okay. So remember these calculations. We will be getting these right numbers. Okay. Now let's move to solving a business problem. Okay. Using all this, we have to try and estimate the population parameter. We're talking about a retail store again. Okay. And the management wants to launch an offer. Any business, do you think they will directly launch the offer? I'm running a business. I just think of giving an offer. Okay. First place, why should I give the offer?
To attract more customers.
To attract more customers. Okay. Very good. But will that solve the problem? If I attract more customers, will that solve my problem? Why we are doing business in the first place?
Purchase should be more.
Profits should be more. Revenue should increase. Profits should be more. Right? But if I say offer, what is happening to my profit margin? See, if I'm selling a product at $100 or 100 INR, okay, let's imagine that we are getting $20 as profit. Okay, let me write dollars. If I have some product XYZ, if I sell it at $100, I'm getting $20 as profit. Now, to attract more people, I would say I will give offer to this product. What I would say, I would sell it at 85% rate only, 15% discount I'm giving. So what will be my product? $85 cost, right? Now, what is the profit margin because of this? Only $5, isn't it? Will my investment, right? Will my business break even out? Will I be able to get all the return on my investment and move to profits? May not be, right? Because of this reduction in the profit, I may not be able to go to a position where I make my business into profits. So offers, when any business is releasing any offer, there will be a lot of scrutinizing happening in the back end. A lot of computing happens to see whether we will get the ROI. In fact, while you want to give an offer, you'll do a lot of promotions as well. Even for that promotion, you need to invest. Right? So a lot of cost is involved when we are giving any kind of an offer. Same thing goes for this business as well. Our retail store also has the same problem. Okay, that's the case study that we are discussing now. Always remember that whenever we say offer, there will be a lot of calculations in the backend. So question again, does this business jump in and give the offer without properly analyzing things?
No.
No, right? Obviously, no. They will have to do a lot of analysis in the back end. They will have to check what would be the ROI, when we will be able to get the ROI, etc., etc. And based on that, the offer price or offer is also defined. Right? If I'm selling a product at $100 and making $20 as profit, 15% discount may not work out. Maybe only 5% discount would work out. Right? We don't know. We will have to look at these kind of computations. That is what we are doing here. Now let's imagine we want to launch the offer. We are the business heads. This is our retail store and we want to launch the offer. So what is our default assumption? In this business decision scenario, at this point where we have to take a business decision on whether we have to launch the offer, what would be your default assumption? Or what is your current condition? Status quo condition. Status quo, right?
Minimum profit should be there. So
No. We are not putting any analytical brain here. My question, let me rephrase my question. Probably I'm not putting my question correctly. You're doing some business, right? The retail store, and you're selling the product at $100. Okay. And your business is running good. That's the understanding, right? Yeah. That is the reason why we are doing the business. So your default condition is that business is running good. Now we want to make some changes. We want to bring some alternates. Alternate options are being brought into the business. That means you are changing the way you are running the business. Some change. What we generally say about a change in an established business, is change good or change not good? In an established business or the current condition, whatever the businesses that we are running in, what would be our default practice or mindset that we will have? In the business lines, I'm saying. Your current condition is this. Now we want to make some offer and make some change. Is change good or not? Say something, there are only two answers. If you say something, then I will respond back, right?
good.
Change is good. Okay. So you're basically saying change is good. Anybody else who wants to contradict this or choose the other option? No? Okay. See, whenever we are dealing with a business, say for example, these are the sessions that we are having, right? I'm conducting the 7 a.m. IST session. Now you're used to it. This is our daily practice. This is something that we are doing on a daily basis. Now, if I want to change, I want to alter this to 7:30 a.m. Is it easy? Can I simply change this? From tomorrow, we will connect at 7:30 a.m. IST. If I say this, will that work out for you? This is an established process, right? Don't you find a lot of things getting altered because of the small variation that we are defining? Making sense what I'm saying? So if I talk
Yes.
about a change, if I want to bring in some change into a business line from whatever is the current situation, our default response will be what? Change is not good. Why? Because whatever we are doing right now is good. We are adapted to it. That is why the business is running. Right? So our default assumption, remember these words, okay? I'm specifically saying default conditions or status quo and all this because the next topic that we are going to discuss is called as hypothesis testing, which basically allows us to do the inferential statistics in the first place. Okay. Hypothesis testing is one of the very, very important statistical computations that we do. Okay. So here there is a business challenge. What is a business challenge? Should we launch the offer or not? The default condition is always your current condition, or however the things are running, right? The status quo condition. And that basically prompts us to say, no, don't launch the offer. I don't want to make any changes at this point of time because my business is running good. Okay, that's our default mindset, isn't it? But we have to now statistically prove that if I make some change, then I will be getting better benefits. So I have to somehow show that if we make the change, then the business will grow better or the business will do better. Right? That is how we have to prove. Now, in the business lines, in the practical world or real world, we will have to get those numbers in order to prove that yes, it is better. But what if it would have not been better? And if you're launching the offer and then analyzing the scenarios, what happens? So you're running at $100 and you decided to give 15% discount. So this cost comes to $85. But this scenario is actually bringing us losses. So would you experiment on the business line and then burn your hands, go into losses, or first you evaluate the situation and then launch the offer if it only gives you good results? Analyze and implement, or implement and analyze? Which is the process that we basically go?
Analyze.
and implement.
It's obviously analyze and implement, right? We always have to go with this. But how will I get data if I don't launch the offer in the first place? Yeah. How will I get the data in order to prove that this is correct or this is wrong? And if I have to analyze, I need data, isn't it? This is where we do pilot projects, POCs, right? One-off experiments, etc. So here also, the retail store, in order to decide whether the offer should be launched or not, if they have 100,000 customers, they will not release the offer to everyone. They will do a sample experiment, maybe at one of the branch where they have 200 customers. Or maybe they have randomly chosen, this is one store, assume, where we have 100,000 unique customers. Okay. So here, maybe based on their membership that we have, right? Membership details that we have, randomly picked, always remember randomly, right? That's the default as a default way to do the sampling. Simple random sampling is performed, and randomly 100 people were sent with a specific discount coupon, offer coupon, only for these 200 randomly chosen people. Because we need data for experiment whether the offer would, right, do better or not. Now, when we give the offer, what happens to the retail store? By default, what happens when we give the offer? Will it improve revenue, profits, or will it improve sales? What is the underlying motto of releasing offers?
Sales. Increase.
Improve
Sales, not the profits. Okay, not profits. It is the sales that we are going to target. So here we are looking at whether overall will customers increase their purchases or not. Overall. Okay. So we are giving offer, and what did we do? We analyze the customer purchasing behavior for, let's say, 1 month. So from this 200 people, these are our core sample area, right? Sample of interest sample, right? This is population 100,000. This is my random sample. This is the area of interest for me now. So we are closely monitoring how much money would they spend in the retail store. Each customer is spending differently, and we are getting 1500 as the average purchase. So how do I represent this? Symbol. What symbol should I write here? I have mu, I have x bar, I have sigma, I have small s.
Mu.
Sales,
Average
so it
mu.
would be X.
This is sample. We are focusing on the numbers on the sample. This is my population parameter, right? Size, population size. Capital N is 100,000, small n is 200. So what we are computing or what we are capturing is for these 200 customers. So it would become X bar. And we've also calculated sample standard deviation. What is the symbol for sample standard deviation?
S square.
Yes. Yes.
S. S square is sample variance. Standard deviation is S. The population standard deviation is also computed and given from the previous such offer launches. Not this offer, but some previous experiments when they were doing. Sorry, my bad. They found out that the sample standard deviation is so much. That means from customer to customer, there is this much of variance or variation. So these are the details that we have now for our sample data. Okay, let me erase all these things. Now, given this, what we need to find out is if I give offer to all the 100,000 customers, will we get profit or not? That's our underlying point, right? And in order to identify the profit, I will have to see how much purchases are the customers making. If the purchases are increasing, only then the profits will increase. In this case, right? So if sales increases beyond a point, only then my profits increase because of the offer that I'm giving. These calculations will be done in the back end. Okay, we'll have some numbers. So we are trying to now analyze whether the purchases increase for these 200 customers if I give offer. Okay, maybe the purchases should be around $2,800 to $3,200 on an average. Maybe. Okay, I don't know. We're basically, sorry, I'll have to give this number, right? From $1,500 we have to talk about. So maybe I would say $1,300 to what is this? 1,500, 200 I minus, so $1,700. I'm averaging it out. This is average. I'm taking $200 this side, $200 that side. If my actual purchases fall here, this is what we are estimating on a right random number. But when we do the calculations, our calculations, right, business people do a lot of these number crunching. What they found is if on an average customers make a purchase of at least $1,600 every month, only then we will be able to make the profits. Okay, assume if you're giving offer, the overall average purchases should be so much. So this is what we have to find out. This is our mu. But we cannot get this number directly. So we are doing the sample statistic. And when we did sample statistic, we got 1,500. Do you think I will get exactly 1,500 purchases on when we release this offer for all the 100,000 customers? Can I estimate the population value as 1,500 based on the sample calculation? Can I do that?
No.
Why?
The sample is less, very less compared to the total number of customers.
Not really. That's not the right answer. Answer is correct that we cannot directly estimate 1500 for population standard population customers, right? 100,000 customers. Why? Sample size is recent enough. We cannot say sample size is less. What else? What is the other reason why we cannot directly estimate that the population also has 1500 average purchases? We are discussing all
The
this.
deviation.
Sorry?
So the deviation would be more.
No. Sampling variation concept we discussed, right? What if I would have got a different 200 customers sample? Do you think
Different result.
at this 200 customers we would get 1500 also?
Probably a different result.
Exactly. Sampling variation is there. Based on just one sample, we cannot conclude for population. No. Why? Because there is variation. If I take different samples, my sample statistic will vary. This is the problem. To overcome this problem, what we are doing now? We are computing the variations, which is represented as standard error of the mean. We are bringing that variation of the samples into the computation. This is X bar, point estimate. We call it as point estimate. But this is varying by how much? If this is my mu, what I calculated is, let's say, X bar. But this is varying from the mu. What is that called as? Just now I explained.
Error. Margin of error.
Standard error. Standard means average, okay? Remember that. Standard error is what we need to bring in. That standard error formula?
Sigma by square root of n.
Yes, sigma by square root of n is the formula of standard error. But along with this, I also have to associate confidence, which is represented as z at 1 minus alpha. I am bringing in the variations. We call this variations as margin of error, which will be added to the point estimate. This calculation has to be done, which gives us an interval, which we call it as confidence interval or interval estimate. Interval estimate. We are estimating for population, right? This is nothing but we are trying to compute mu, population parameter. What all things we know? We know small n. From this formula, we know small n. We know X bar. We know sigma from the previous launches. What else we need?
Z value.
Z at 1 minus alpha. What is the industrial standard? 95%. What is that 95% value?
1.96.
Yes, plus or minus 1.96. So we'll have to simply substitute the values into this. 1500 plus or minus 1.96 into sigma is how much? 2500 by square root of 200. This will give me the range for mu. Okay. Now, if I know that this range is carrying the $1,600 or $1,700, whatever we benchmarked, right? Based on our calculations, we are trying to see whether we will be reaching that standard or not. Or if I get this range, this calculated at 95% confidence, if I get some range, we will see whether this 1700 is falling in this range or not. If it is falling, then we can say we are able to achieve that. If you are getting 1700 falling here, outside the range. Yeah, let me draw this again. I'll draw it and explain here. So we basically found that from the business, we found that there is a standard which is average purchases should be greater than 1700 to get profits. Okay, this is our standard benchmark. Now, when we estimated here, we got some range. Okay, let's say case one. Case one says our range is, let's say, $1,400 to $1,600. Assume, just for discussion purpose. This is your mu. So if you look into the diagram, 95% confidence. This is 1400. This is 1600. Where is my 1700 target, which we want to achieve? Outside the range. We need to have at least 1700 to get into profits. So should we launch the offer based on these calculations? What do you say? If I'm launching the offer for all the 100,000 customers, it is estimated that the average purchases will be in this range, 1400 to 1600. But what is our business standard? Business standard is assumed to be 1700. So are we meeting the required standard if I launch the offer for 100,000 customers?
No.
No, right? Sorry, go ahead. Yeah, please go ahead. Somebody was speaking. Was it Priyanka, Archana? Who was that?
No, I said just no.
No.
Same.
Okay, okay. All right. So yes, the answer is no. We are not reaching this target. So what should be my business decision here? Should we launch the offer or not? That was the business problem that we need to solve. What should I say here?
Not to release the offer.
Do not launch the offer because it is not giving us any profits. This is case one. What if I found out that the average falls in a range of, let's say, this is 1500, right? So let's say we got 1250 to 1750. Are we getting into profits? Should I launch the offer now? $1,250 to $1,700. Our benchmark is 1,700. Should we launch the offer or not? What happened? Sudden silence. Yeah, guys, say something. Oh, my bad.
I would say no.
You would say no. Why? Answer is correct. I'm giving you a hint. Answer is correct. But why would you say no?
The range is more. I mean, from 1250 to 1750. So,
Okay.
and there would not be a scenario where it would always go above 1700.
Okay, I can take that. But see, this range is basically saying whether the value that we are interested in is falling in that area or not. That's all. So it is like equal to 1700. This one is less than 1700. This one is like equal to 1700. Okay. If it falls in the range, we are saying yes, 95% confidence that the value is equal to 1700. So if you are getting exactly 1700, that is the break even point, would you do the business with break even points? It's like no profit, no loss case. Would you continue the business if that is the scenario?
No.
No, right? I mean, if I'm investing $100, I want at least $101. That is the profit. If I get only $100, there's no point running that business. I would rather focus somewhere else. It's not like I'm doing a handshake. $100 I invest, $100 I get. There's no point, isn't it? So even this would not be an ideal business case. The third case is when you have a range which basically is showing that the customers, right, average sales for 100,000 customers is falling such a way where your 1700 is falling this side. Okay, you get more than 1700. Your value should be greater than $1,700. That is when you get profits. Okay, so in that case, you will say yes, go ahead and launch the profit. Here, this is the third case where you get 1700 here. So maybe you get 1800 to some number. All right. So this is how we have to interpret our results, and then based on these results, we'll have to make the decisions. So if I have to summarize, I have a business standard. What is that? 1700. Okay, we are basically putting some standard. So in this scenario, we would basically come up with the default condition is no. But when we will go for no default decision, when there is no profits, and when we will get profits, if our average is less than or equal to $1,700, then our decision is no. But if we found that the estimated parameter is greater than $1,700, that is when our decision is yes, launch the offer. Clear? So confidence level, we will have to take 95% by default unless until it is explicitly mentioned. And when we use this, right, it basically says that if we repeat this experiment 100 times, 95% results or 95 intervals that we are getting out of 100 intervals will have the true parameter, that is 1700 that we are talking about, within that range. That is 95% confidence means. Okay. That means the chance of going wrong out of 100 times, 95 times I am correct. So whatever the estimations that we are talking about, the intervals that we are calculating, it is always for parameters, not for individual members or sample data points in the population. It is for mu, population always. And this is the limit that we get, which is called as confidence interval, right? The range, lower limit and upper limit. Right? This is where our parameter is likely to fall. That's the reason why we put confidence interval, right? Probability. There's a chance of 5% that we may go wrong. Okay, remember that. Yeah, so this is basically how we do the computation. This is the formula that we use, confidence interval formula, in doing this computation. X bar plus or minus z at 1 minus alpha and sigma by square root of r. Okay, this is point estimate plus or minus. This is called as margin of error. Margin of error is nothing but standard error with some confidence. Any questions in this? I've extended the duration, but it was necessary. Any questions in this discussion? Okay, so we will be continuing the same point tomorrow. Okay, we are trying to compute population parameter using all these statistical formulas and all these center limit theorems that we have studied. This is because we will not get population data in the first place. We'll only get sample data. Hence, we will only be able to calculate statistic. Using statistic, we are computing parameter. But in this formula, we also have another parameter, sigma. This is population. If I don't know population data, how will I know this? This is an assumption that we are making, but in practical cases, what if I did not launch this offer at all? Right? So how can I get population data, population parameter without having population data? And if I know population data, I will be able to know population parameter also. Right? So how do I fine tune this equation to remove this population parameter? That is our discussion point tomorrow. All right, we'll meet and discuss further on the same concept. If you don't have any questions, then thank you so much. I'll wind up for today. Any questions? No. Okay. All right. Thank you, guys. I'll stop here now. I'll see you tomorrow.